Summer school is. Let me tell you a story about Jack and Diane. No, summer school. When I was a new professor here, I did 450A, math 450A in summer. You know what class that is, right? 450A. And
it's really hard.
It is. I look. Okay, look. I was so lucky. I took it summer at UCLA, and I had the best teacher in the entire university, and I loved it. It was just, and he had this policy on tests. Every test had options of what, which the problems you had to do with. So you had like 5 problems that were problems type, like problems in the book, and 5 problems that were to produce the proof that you had memorized beforehand for things. And you could choose like 3 of each. And I really liked that. Or no, a total of 5. I really liked it because I felt I was better at reproducing proofs at that time when I was younger. And I felt like I learned the stuff that way. And he said that people have different abilities. Some people are good at doing exercises, problems in the end of the chapter. Other people are good at digesting those proofs and then presenting those proofs, in a time pressure situation. I don't know how you feel about that, but I felt like his approach was sensational. And but anyhow, so I took it in summer, and I'm glad I did that. Okay, but back to the story. Somebody was taking 458 in the summer, and it was the 4th or 5th time they took the course. This is before they put the limits on the repeats, and this person had tried 4 different CSUs to pass the course, and this is the last course they needed to become a math major, to graduate as a math major. Oh my gosh, I just couldn't believe it. They shopped around to find the easiest one. They found me. But those are the old days. CSU doesn't work that way anymore. How many times do you get to take a course? What's the rule?
Pretty sure it's 3.
It's 3?
Yeah, after 3, they start telling you, you need to figure something else out.
What do they say? Can you spell the word ringer? R-I-N-G-E-R? No, okay. Okay, so you smile. Good. Okay, so where the heck? Okay, I've been just whatever. This is a very challenging year for me. So I've been slow with grading your tests, but finally I put together, with the help from some of your papers, to make sure my answers were right, a key. Did you guys see that posted? Okay, so there was some departures from my key has some departure from some of the papers, and I just wanted to touch that briefly. There was something about the problem about the expected number of inversions for a random permutation, right? Or an ERP hit it, and then the ERP is spitting out random permutations, and what's the expected number of inversions? Okay, and I want to see where this shakes out in the big picture of things. So I went to Slater and Chegg, and it's right, it's all there. It's there in full living color. Okay, so they produce, Chegg produces a solution. But what fascinates me is the key to it is to get the expectation of that I and J, 2 letters in the permutation have been switched. And there's no mention of how to do. They just say, okay, it's a half, it's a half, it's a half. Or they mention symmetry, which you're really only allowed to do if you're a physics major, in my feeling. So how do we know that I is less than J? And half the times I'd have to look at all the permutations. So, so it's the permutation of n things. So it's the permutation of this. Let's see if I got this right. And we're looking at 2 special guys, I and J. Okay, I'm looking at I and J. And let's just count the number of permutations that have I less than J. And if it's n factorial over 2, then we know that it's a half. The answer is a half, right? We've just got to make the lousy count. So how many places can I put I and J here? So you tell me. So there's going to be some permutation. Random. So how many places can I put I and J? How many locations? Well, I have n, right? So what do I need to write? So I just want locations for I and j.
I can go in n places. J can go in n-1 places. So n times n-1.
Well, let's just reserve. Okay, let's reserve the 2 spots for them. Okay, so there's n spots. We're going to reserve the 2 where they're going to go, and I'm not going to multiply by 2 because I'm assuming that I is less than j. Okay, we're going to check that. Now, how many places can the rest of that junk go? How many more letters are there? Well, there's n minus 2, right? So n minus 2 factorial. Are you following me, or am I going off the deep end here? I'm just going to count all the ones that have I less than j. Okay. So put the I and j wherever, this can go anywhere, and choose 2 ways. And then the rest of the numbers can be slapped in there, n minus 2 factorial. What is this equal to? Let's do the math. Maybe I'm not thinking clearly, but it's n factorial over what? It's a weird n. N factorial over what? 2 times n minus 2 factorial times n minus 2 factorial. What's this equal to? That's half. Half of the permutations, assuming, the generator is putting them out all equally likely, but half of them have I less than j. I don't see any. It's funny in the Chegg and the Slater, they don't do this. I don't know what they just. They don't do anything. They just say it's obviously a half. I think you got to something has to be done to show that. I mean, it's just my opinion. Rather than just copy the Chegg thing, it's probably been up there for 20 years or something. Because this problem is from CLRS. Okay, we good on this? Okay.
I mean, I think part of it is just we didn't think to do it that way. And I definitely agree with you that I feel like it feels like a leap of logic, but it's just like, how do I show it? I guess this is how.
This is one way, but if you're, again, to give...
Well, we didn't have a way. So other than it feels right.
I did read your paper, and you said if you're a physics major, absolutely it flies. It's symmetrical, because you could say something like, well, it didn't matter. We could have switched I and j, and you got to get the same number. The only way you get the same number,
right? Well, that's kind of how I visualized it. Is okay. Well, if this one exists, well, then the other one must also exist, and there's always a pair. So I guess.
Well, no, you can't. You have a certain number of I less than j, right? But you could also have a certain number of j I greater than j. But they have to be the same, because I get
right.
Your argument is okay. I'm probably giving it credit because you mentioned symmetry. It's a powerful word,
Right. Yeah. I couldn't have any other way to. I couldn't think of any other way to say it other than the other one must be there, and there's always a pair.
But
that's all I can think of.
This is actually a deeper discussion than you may realize, and I'm not making any of this up. If you go to CLRS and you see their section on ERPs, they prove stuff that seems pretty obvious. They actually go ahead and they're using the probability that we learned in chapter 3. They actually use all the machinery to prove that these ERPs are ERPs. It's fascinating that so much has to be done to establish something that seems so obvious. And which brings up the other thing, the ERP problem. Do you guys remember that it's been so long since you turned them in? I feel like a crappy teacher to just sit.
Yeah, I'm like, hold on, I need to go over the tests again. And there definitely were things where, work was done very quickly because we were running out of time. Uh-huh. Whatever, it happens.
Sure. I hear you, but yes, and I made this. Actually, I have to come clean here. I used your paper to help me do the instance.
Not everything there is right, though. I know it's not. There were things that I'm just like,
okay, let's talk about instant insanity without going insane. There were 25 possibilities.
Oh, really?
In total, right?
Oh, okay.
There were two wild cards. I think this was B wild card, and there was E wild card. So definitely between the two, since you have 5 colors, right? There was 25 total, right? Okay.
Right.
So you could eliminate, you can't, you have to make sure you don't have too many purples. I mean, that's the major constraint. You guys remember this problem? You don't want too many purples because then there's no solution. And I forgot, if I believe it was E, if you make E a purple, you're going to be guaranteed to not have a solution. There'll be too many purples showing.
Yeah. I mean, I didn't write down the reasons. I didn't write
You
down
don't have to
the
have reasons. You did eliminate it. You actually did it. You actually didn't show it. I mean, I think you must have known there'd be two. You knew how to do this. So that brings you
Yeah,
to 20.
I did go through all of them. I went through. Okay, I went through all of them. I didn't feel like I had enough time really to really explain the logic behind the ones.
Oh, no need to explain. You just need to answer. No need to explain.
Okay, all right.
No need to explain.
So,
but I think you got 13 here.
yeah.
So to me, the gap was, from 20, there's 7. There's 7 that have to be eliminated here. And of course, you have to show these 13 work. I was able to do that. I did that. I did all, but I did 16 of them. Okay, so yeah, I have a way of doing it. It's different than the graphical method. So, but I'm confident that that's correct. The question is the 6. There's like 6 here in the gap, and I checked one of them. So yeah, I mean, it's possible that one of those it actually works. I doubt it, but it could work. It could work. It's not that easy to cover all these cases unless you have access to a program that simply solves it out. You put in the inputs and just crunches it out. Let me just put it up there then, since we're talking about it. Did anybody get a different answer, or they got fewer or more that worked? Does anybody speak up or no? I mean, it's okay. Maybe.
Yeah, I got 7 that worked.
Oh, you got fewer than 13.
Yeah.
I checked these, and I'm trying to think how would you,
I didn't like share my answers with anyone.
I trust you. I trust you. If you did, everybody had the same answer.
Yeah, if other people have fewer, it's just that you couldn't find a way to make the other ones work. Like I wouldn't be surprised that there are fewer.
It took me an hour to do this. I mean, I did these. It took me an hour to do it, but I have a different. How to explain? My method is different than what you're doing. I know that trying to remember now. There's 2 cubes where there's an opposite. One of the opposite pairs on each one can't be used. So there's only 2 options on those 2 cubes, and I looked at those first. Okay, and again, I'm looking for a solution, right? So that changes how I approach it, also, right? So I was able to, I'm not infallible, but I did them, So I feel confident about this.
The way that I thought about it was, it's kind of like Sudoku, where you have to fill the color, and there's like a limit to how many you can have for each color. But I'd be really curious to see the ones you got, if you have them, because I actually went ahead and I made the cubes themselves.
Yes.
To double check answers.
Yes.
At this point, I can share my work.
Well, let's do it this way. Okay, look, I'll show you my method. So why don't you give me one you think doesn't work you said, you've got one that,
I did pairs.
It could be one that we don't.
I did opposite side pairs because that's consistent. Like on opposite sides, the faces, I counted them as pairs.
Yes, that's how you do it. That's how you do it that way either way, if you graphically or not. Let me grab the key, or you guys tell me. Let me find the test. Okay. This is going to be a little difficult here to get everything straight. But I'm going to, so for A, trying to avoid this bad thing. So what do I have for A? Purple, yellow, and red, purple, red. So B is black, yellow, so green, yellow, and it's got this red question mark. And C is green, 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 black, green, and black, red. And D is green, yellow, black, red, and red, yellow. And now E is the crucial thing because, okay, so remember, this one, you guys understand, this only has two possibilities here, and the same with this. So this has black, purple, and purple question mark. So where's my B? Okay, this was a question mark. Okay, now let me try to pick on one of the ones that the gentleman is saying he didn't have. So what were the question marks that one that you said it wasn't, but on the key it shows as being okay. So let's put those in. What were your choices for the question marks?
For the colors?
Yeah, I want one that doesn't show, that shows as solvable on the key, but you have as not solvable.
You know what? I need to double check the key because you have them as pairs of colors, right?
Yeah.
Yeah. Let me double check it really quick. You know what? Just to not take up time, let me just go really quickly through it and I'll come back to you.
Oh, well, I got it on the board. That's the only thing. So I wish I just had one case that is in question. I've gotten, so what's one that I think has a solution? Well, maybe that's better. Okay, so I have that if you have red with E, so if this is a red, then you can pair it with anything, okay? So if this is a red, then I can pair this red right here with anything, okay? That's for instance, maybe that's not true. So even a purple, so the claim is that even with a purple there, I can find a solution. This is sort of surprising because you don't want any more purples in this thing. So that must mean what? If you don't want any more purple showing, are you following my logic here? So if you don't want any more purple showing, what must happen at this point?
You can't have the purple ones?
Yeah, we can't, right? We can't use it. So you can assume that this is unusable. Okay? Assuming I've had enough coffee to think clearly, okay? So now, can we this is not, I'm not using the graphical method, but I'm on the spot here. Can we solve this puzzle as shown here? And what is the technique? Notice that I've got a reduction in possibilities because these are just two choices here. But 2 to the 5 is 32. So here we don't want to, you know what I mean? We don't want to. What can we eliminate? If you take black, we have to take. So one of the solution. Okay, one of the solutions has to have this. Okay, you have to have that, right? Because this is no longer in flux. This cube has to show 2 opposite pairs, right? You good with that?
Yes.
And but it's black, so then it must be green here because you can't have a third black. Now the fact is, it's got 2 blacks and 2 greens, so that would force it. I hope this works. If it doesn't, you guys, that's life, It has to be this, right? Do you see my technique? So now what? I can't take this because I got 2 blacks. So this thread must take that. And what do I do now? Tell me what to do.
But this is for the specific case where the random color is like a very specific color, right?
Purple and red, yeah. There's two random colors. One is purple, the other is red. The purple one is on cube B, and the red is on cube E. I was claiming that this was a solvable puzzle.
Oh, okay.
But
Well, I mean, you
I'm
would
telling
have-
you my method, which I think is a little faster than drawing the graphs, but I don't know. So you guys, look at what I'm doing here. I had no choice. Once I said that one of these was black, these were all set. Now what about here? Well, I've got two reds already, so this had better work for one of the threads. It had better work. Now the key is, and this is my life's hanging by a thread, right? I've got to see if I can pair this thread with another one, with a matching one. I don't know that I can, but I do know the options are limited, right? The options are limited. The other thread must have that, right? And it must have this. I don't know. And what else must it have? Believe it or not, it's going to have this because that's gone. Now, let's take a look at what's been set here. It looks like I've got, unbelievably, one of each color. So how are we going to, is that possible? Purple. No, I've got purple. I have four colors have only showing up once. So how are we going to fix this? I don't know. It can be done. I need to be careful. I need reds, right? What should I do? Should green, yellow? What if I took, I don't know, maybe not. Does this work? Does that work? Is that a solution? Well, how do you check if it's a solution? I mean, each of these threads has to have each color showing up exactly twice. Is that the case? I'm not saying that I did this real time. I'm not reading off notes here, so I could have very well made a mistake. But what do you guys think?
Yeah, I think that one is a solution.
Okay, well then, so this rule, I think it was the 20, right? The 20 it's a 20. So this says that one of those 20, because the potential is good, we can check this off. So that means we still have to search. Yeah, we can search all the others, and apparently you end up with 13, apparently. But this is how I do it. So, and can I ask you the question, is this slower, faster, or different? I don't know. How did that compare to the graphical method?
I mean, honestly, I can look at this method and kind of still do it the same way that I was thinking about it. Like the way that I think about the ones that have boxes on is starting at the bottom.
Yeah.
You go from purple to black.
Mm-hmm.
Okay, well then you have to then go from black to red. So there it is on C. And then from red to purple, and then you've done it. You've got a cycle.
Mm-hmm.
And then for the other one, you go from green to yellow, and then from yellow back to green. So the letters are just the path that you take to get from color to color. So
it has to be
it's still
cycles.
the same idea.
Right, it has to be cycles. It has to be cycles. But to me, you see, when I did I knew that one of these had to be black, right? Because this is gone. And that put a big constraint on what else could be, because a lot of these, the cubes have black in them. So that's what I was trying to get at. Okay, I'm sorry to take all this time on this, but I suspect 13 is okay. But if there is one in contention, I'd certainly like to see it and see if I could solve it. Okay, I didn't know. And this evidently wasn't the one that was in contention.
But that's also why I wrote my cycles down. So unless the cycle was wrong, you can actually go and yes, there it is.
Well, the problem is, just from experience, is sometimes people will write down the graph incorrectly. And so the cycles are there, solution, but they go back to the puzzle. It doesn't work because
sure. That's absolutely true.
That's the killer.
That sometimes it does, you write it down, but you can't bring it back.
Right.
But I'm, hopefully.
Well, did I tell you? Go ahead.
Just assuming that it's right.
Yes. Did I tell you? I told you the story, right? Of the guy that got this graphical method. He was 17. His name was this. He became a famous graph theorist, Tutte. But he didn't put his name on it. When he was 1947, he published the paper when he was 17 years old. He didn't put his name on it because he felt that the result was not significant enough. Go ahead. Who is that? Ernesto?
Oh, sorry. Yeah. I'll just double check some of the ones that you mentioned, because I didn't account for maybe the possibility of, the color pairs could work on either of the random faces.
Oh, I mean, you could switch. You could switch them, maybe. I don't know.
Yeah. So
This
I
one-
got to double check them.
Yeah, this one you can't switch, but I do know that you can go from experience with this puzzle, giving it in 42, you can go black, yellow, and yellow, black. That's a switcheroo. That both of those work.
Yeah, I suspect you're probably right on it. You know what? In fact, you're definitely right on it because I didn't think about swapping the colors.
Okay, don't give me zero credit. Zero. Ames group did it. They generated the 13. It's just, of course, I got into it and I realized this is a lot of work. So I just opened up their, paper to see, well, is this looking at, of course, I had to verify that the 13 they claimed were solutions, but I didn't do it. They did it. So
the saddest part was I spent 2 days on it and I didn't even think about the possibility of that.
Well,
I spent 2 days on it too, probably a total of 10 hours on a single problem.
Nice.
So now now you can put that on your resume. You say experts on ERPs and and instant insanity. Okay, guys. Now the other issue. Sorry, I'm not trying to pick at you at all on the test, but I was confused about the ERP problem, and I'm just not sure why you. I'm just not sure what happened there. If your algorithm, if it was this, if your ERP was permute with all, what does that mean? Well, you start with say 1, 2, 3, and you have 3 possibilities here. You can permute the 1 with itself, with 2, or with 3, right? So that accounts for these 3 things. You permute with itself, you get 1, 2, 3, or 3, 2, 1. Okay, these are the 3 possibilities. This is not the one I gave you, but I'm saying suppose it was permute with all. Just suppose. Okay, what would be the next step? So this is I equals 1, and I equals 2 of this algorithm. This doesn't have a double hit in the for loop. It just has 1. You permute from the ith component with any one of the other with any one of the 3. So what happens with 1, 2, 3 now? Tell me. So 2 could permute with 1, and what would I get? 2, 1, 3. It can permute with itself, or it can permute with the 3. You get this? And this would be one that just goes down like this. This is the end of it down here. Permute with all. Instead of the one that I gave you on the test, which was also a double hit, it was permuting with something itself or to the right, correct? Do you guys remember that? You switch it, you swap with itself or something to the right.
I thought it was permuting. I thought it was swapping with anything other than itself.
No, that's permute with all.
Wait.
Can we look at the code for a second?
Yeah, but permute with all, it's also allowed to swap with itself.
Oh, yes. But you guys...
In the problem, I remember it wasn't allowed to swap with itself effectively.
Yeah, but you have I there, right? So you're at the ith component when I equals 1 in that loop, and it will permute with itself or something to the right. And it will do that twice. Then the next time through the for loop, it'll be a 2, right?
Are we talking...
Well, if that's the case, then we misunderstood the problem.
Oh. Okay, so let's pull the code. Let's pull the code.
If that's the problem I'm thinking about, that's not how I understood it. So I might have been wrong about it.
Well, let me see what the. Let me dig for the code here. It's funny. Everything comes down to coding. Where is this? Where's my? Oh, finally. Okay, let's take a look at this code. This is the issue. So what do you call this? Permute? Let's write that in the washout. Okay, so what happens here? For I is 1 to n, what happens? Swap a sub I with what? A sub random number between I and n. Okay, and then you do the same line again. So what do we have? So you're going to look at, you're trying to see if this thing is,
I see.
let's
I
just,
might have missed that part of it. I was looking at a different weird part thing about it, which is that, what am I trying to say? No matter what. Wait, fuck, I don't remember.
okay, look,
Look at it again.
that's okay. It's okay, Ethan. Let's hold on a second. Let's ask the other people. Did you guys notice this I here? Maybe that was the problem. So when I is 1, it's the first component swapping with itself or the other two, right? When I is 2, it's the second component swapping with itself or with the third one. Does that make sense? I'm just trying to figure out what about this code confused you. Do you see that that's an I right here? It's funny. Everything comes down to code at some point. This is the way science is, whatever. Okay, that I there is critical. If you don't put the I, you get something like this, situation like that. Okay, is it clear now? You guys just misread the code? So
I guess so. I mean, okay, so keep in mind, I don't have any coding experience at all. So I was very confused to begin with, and I had to have my group members explain it in the first place. And I kind of more or less I took my hands off of this problem a whole bunch.
okay.
It's like, you know what? I'm
Did you have a
struggling with
CS?
understanding.
Did you have a CS major in your group?
Yes, and so I let them deal with it.
Right. Okay. Let me think for a second here. Do you guys see that this is fundamentally different than Permute? Let's just try to explain it so you guys are comfortable with this code. This is fundamentally different than this. This is swap with anybody. It goes through 3 iterations. Swap with anybody, okay? But it looks the one that you're swapping with it goes the first component, the first loop through, the second component, and then the third. Okay? Are you guys good with this generation like this? So 1 is with itself with 2 and 3. That makes these 3. Do it again. I equals 2. Now you're looking at the place. See, the place you're looking at here is here. Here you're looking here.
See, I might have missed that fact that it has to be anything to the right of it, but
itself or anything to the right. Yeah.
And there was another assumption that I made, which was that the random choice was never I itself. I assumed it was swapping with something other than a sub I each time.
Okay, you should have checked that with me. Yes, I see.
Yeah,
you should have checked that with me. That apparently this is a pseudo. It's in CLRS, so it's a standard. Must be a standard pseudocode notation. But I can definitely see that could have caused problems.
Yeah. I probably should have checked on that.
It's like a range, right? A range of values.
So I just wanted to say because I made that assumption. Something else came up that made this non-uniform in a different way, and that's because basically you're swapping with a sub I something with something else, and then you swap a sub I with something else again, but you're never allowed to. But a sub I is never allowed to be swapped with itself.
Yeah, got it.
So you get the thing that if you have a really small distribution like this, it stays exactly it tends more likely to stay the same.
I hear you. But do you notice one thing about, look, suppose everybody hears what he's saying, right? If you're only swapping to the right, your code would have some trouble on the third time through, right? Because there is no right of where you're at. If you're in the third component, the only thing you can do to keep this thing making sense is to swap with itself. Because there's nothing in the fourth. The size of the array is 3. So if you tried to implement that, you would have gotten some error message. But that's okay. Now that I know, now I understand what's going on here. Okay, because I wasn't sure when I was looking over skimming over the papers, what was behind that. But can I do this? Can I suggest this? Let's look at this problem, which wasn't on the test, but is prominent in CLRS. Okay, what's the situation in this case? Now you're swapping with everybody, right? 3 times through. Can anybody look at this and forget? It doesn't matter if you're computer science or not, because the reason this doesn't produce an ERP is pretty fundamental. Why wouldn't you have an ERP in this situation? So in other words, you're swapping with the 1 with anybody, and here the 2 with anybody, these 3, and then here the 3 with anybody. So your leaves are down here of this tree. Can anybody think of a reason why this wouldn't? This is a CLRS problem. So if you get this, power to you. It's just a simple observation, but it's not what you're probably thinking of. To be an ERP, all of these, each permutation has to be equally likely, right, in the output.
Well, I'm having trouble trying to say it in terms of the graph, but I think some of these operations.
These are all the possible outcomes, right? They're all equally likely. So those. So are we clear? Everybody clear on that? Those are all the outcomes down there.
Mm-hmm.
How do we know? How do we know already, just by looking at it, that it's not an ERP?
So for these equally likely ones, you're allowed to swap with any place, not just to the right.
Yes.
So
that's why it has 3 branching.
Yeah.
3.
Oh,
so
are you clear
on this? Should I slow down? And are you clear on how this works? I just want to make sure, because you're going like this. Does this make sense what the process is? Or should I slow it down and do one?
I understand.
I know you do. But I'm wondering about AIM right now. I don't want
no, I don't get it.
Okay. Let's just do one line of it.
Well, can I the answer to what you said?
Yeah, no, not right now. Because
Okay.
If this is where you start, okay, and you're going to start here on equals 1, so you're going to say I can swap that guy with anyone. So that anyone could be one of 3 possibilities, right? Itself, the 2, or the 3. But those are equally likely.
Okay.
So if it swaps with itself, you end up with this, right? 1 with itself. If it swaps with the 2, you would end up with 2, 1, 3. If 1 swaps with the 3, you'd end up with 3, 2, 1.
All right. And then we go down the branch.
Just do one more. Yeah, let's try this one.
Okay.
So it does it again. But except you're starting with, you're swapping the 2 with anybody.
So were you picking the 2 because it's in the second spot?
Yes,
or just
right. I now is 2. I is 2. So you're looking at the second component in that array of 3. So if you take the 2 and if you swap it with the 1, what do you get? If you swap it with itself, if you swap it with the 3, you get this. Let's just do one more. Let me see how I test you. Tell me what the first one would be here. So who's the I is 3 now? So we're looking to do what?
Swap 3 with the first thing?
Yes, and what would that be?
So we get 3, 1, 2.
Exactly.
Okay.
And what about if I swapped it with the second place?
2, 3, 1.
And if I swapped it with itself?
2, 1, 3.
Now, this is a probability tree diagram, which you're probably really familiar with after doing that super hard problem, which you got right, correct. By the way, so I was stunned, that you guys got it. Very good, congratulations. But that was a huge tree, right? But this is a tree where every branch is equally likely, and these are the outcomes at the bottom. These are all the outcomes. So a natural question is, how many outcomes are there? And they're all equally likely, right? Why are they all equally likely? Because it was randomly chosen who you swap with, right? So if you want, you can put the little 1/3 in here. Okay. So how many outcomes are at the bottom? Ethan knows the answer. He's already got this thing nailed.
27.
Why do you say 27?
There's 3
Well,
times 3 times 3.
Each of these 3 had 3, and each of those 3 had 3. So that's 3 cubed. You're right. So there's 27 down here. 27. It's the same. Did we do the same thing over here, right? Better be the same answer.
Okay, and I think I can see the logic from here. There's 6 permutations of 3 things. 27 isn't a multiple of 6. There's got to be something that's doubled.
Very good. I think Ethan had this, right? Ethan, you saw this, right? Because you started to say it. We started to say this.
Yeah, I think. Well, I'm not quite following what.
But I think you're doing the same thing. That's when I cut you off. But
yeah. So 3 factorial. Yeah. So well, inherently, I'm just looking at the factorial part. It's like instead of raising it to a power, instead of having 3 options and then 3 options and then 3 options, you have 3 and then 2 and then 1.
So look, let's use the blue marker to try to get this point across in case somebody's struggling. You have 27 outcomes, right? Now, for each of the 3 factorial to be equally likely, we need to have each of those 6 outcomes showing up the same number of times, right? So take one of them, 1, 2, 3. How many times would 1, 2, 3 have to show up? Well, it shows up wherever it is. Let's say 2, 3, 1. It's somewhere, something like that. But Abe, go ahead and say it. So now I can't follow it. You got to have. You've got 6 things, right? They all have to show up the same number of times. So the number of outcomes has to be a multiple of 6. It has to be. There's no other way. This is a number theory thing, okay? And what do we notice? That 6,
I see what you mean.
6. You took number theory, right, or something like that. It don't divide what?
I'm currently taking number theory, and it's very hard. I'm struggling in that class.
Oh, you're taking it. So that's why you probably saw this right away, because you're taking that class, that 6 doesn't divide 27.
Right.
So congratulations. We just did a problem in CLRS. It's a pseudo graduate book. But this opens up, guys, and this is the interesting thing about this. It opens up the possibility of a case where 6 does divide it, but it's not an ERP. That's interesting. And I found one by accident where this happens. And the deviation from an ERP is so small you wouldn't notice it unless you had put that code in there purposely. It's a malignant kind of thing, you know what I mean? You were trying to game the system or something. You put this random permutation generator, which is just off by a little bit. And nobody would suspect because it's only 4 lines of code. And I've asked my colleagues about this case, I've asked them about it, say, how do you know it's not an ERP? And they say, we don't know. You have to build up this stupid tree to find out. The deviation is like less than 1%. And in fact, I'm trying to remember, it has
well, that's if there's like a large number of items, right?
Yeah, the number of leaves is.
What algorithm are you talking about that has such a small difference?
My memory is, it's got a 2 in it. Let me just wish I could remember it, but I think it might be this crazy number. What is that? What's 4 times 27?
Yeah.
This is the famous number in the East, right? If you're into numerology, 108's the number, right? It's not 7, that's in the West. In the East, 108's it. So I have 108 leaves, and so I'm trying to use the same approach, and where does it fail? Well, I take 6. The problem is 6. In this case, if you have this many leaves, 6 in fact does divide 108. So you can't use that argument. And I dare you guys to try to find a way to improve it, because you would beat back all the statisticians I asked how to do it. I believe you could base a thesis or a project or an undergraduate research on that case, and to see, well, how do we show that it's not, without looking at all the possibilities? There must be something about something in mathematics you can apply to get this answer. All right, okay, that's the end of that story. Have I finished screaming about the test? Any questions about this? Was there anything else on the test that was? I posted up the key. Did anything else disagreeable? I'm trying to remember.
I just had a quick question.
Yes.
The one about the restaurants?
Yeah. Maybe I did that wrong. Did you guys?
No, I got the same answer. It's just the response that you provided as the answer, like it differs, I guess. And I was just curious if it was.
Oh, well, I could be wrong. Maybe I got the wrong answer. Did you guys double check my key answer against yours, or double check it?
Yeah, it's just like in the question you ask which one's more likely to like, I guess, survive.
Uh-huh.
But as an answer, you said, like a savvy investor, I guess, would put their money on A. But in the numbers, it shows that, I guess, restaurant B.
Oh, then I just
likely.
total brain fart on my case, because it should be the one that's has a longer expected life, right?
Yeah. Okay. All right. I was just double checking.
Yeah, I'm sorry. Forgive me about that. But it's such a small difference that, at least if I did the calculation right, I don't know if I.
Yeah. I got this exact same thing.
If I did it, I would say that how to say this. Okay, guys, this is real statistics here. It's like I'm totally out of my comfort zone. But what were the two answers? Help me out. One restaurant. What was A?
A was exactly 6, I believe,
What was
and
B?
then B was like 6.3 or 6.4 if you round it up.
Okay. Suppose you're a money guy, and you're smart, and you're looking at these two. It really, what happens here really depends on the variability in this, right? Right? I mean, whether 6 is really different than 6.3, you know what I mean? There's different means here, but if you were to make a histogram of the results, it would matter whether this could just be, how should I say, it could be non-significant difference if it's within one standard deviation, but if it's 3 standard deviations away, yeah, then it's something. But this could be absolutely meaningless, the difference of these two. So I meant to say with the savvy investor probably knows how to take the variance or find out how much variation there is. It probably says it doesn't matter whichever one is convenient, to invest in, right? I mean, I don't know. I don't know if this is a significant difference. You understand what I'm saying?
Yeah, if you're in that sense, I would understand, but I was just curious, like answer wise.
Oh, I just blew
curious.
it. My mistake. I'll have to fix. That's probably more than one thing I have to fix, but that's the wrong answer. I should have said a savvy investor would try to find out the variance. What's a customary departure, from the mean here. You get what I'm saying, right? If you have, suppose your data is normally distributed like that. Okay, here's the mean, and somebody says, well, I got this, but notice that really doesn't. It's not significantly different because it's within one standard deviation of the mean. It doesn't mean much. I mean, whether you got this or this, it's typical to get that variation just by chance, right? It's not a fundamental difference. I don't know that 6 years or 6.3 years under these conditions is fundamentally different. You've got to be careful when you use numbers this way, that you don't attribute, small things don't mean, and even if it is significant, sometimes statistical significance is meaningless. It's meaningless. All right, thanks for pointing that out. I'm sorry, obviously I didn't prove what I was writing there, but I'm glad you got these numbers, because I believe that's what I got on the key. So I don't. Did anybody else get these numbers? Okay, I shouldn't. Maybe that's a question I shouldn't ask. But the 6, right? The 6 was pretty standard. It was kind of similar to what we did. All right. Any other comment or question? Thank you for pointing that out about the exam. Well, I should have kept that drawing there. Okay. Any other comment about the key? Exam was long, hard. Volume was high. I got to make the next exam shorter. This is killing me now. This is killing us, right? And
it makes it easier for you to grade too. So
you know what my thing is? I'm sorry. I'm trying to fight this giant, this Czech giant, and I'm trying to find problems that the Czech tutors, not that they can't do them, but they don't want to spend that much time mucking with it, you know. And I think it was pretty successful on at least the instant insanity. I don't know that the Czech tutors probably just said, "Give me a." Well, they use a bad language, right? Give me a something break. Okay, where were we last time? I'm sorry to be so all over the place. You know, it's funny, rabbit hop. I'm a rabbit, right? So it's my sign. No.
we had just started at chapter 5, looking at continuous random variables.
What is the situation? You have a continuous random variable x. You really you have to have this density function that goes with it, right? And you integrate that over a range or some set even, and that's how you get the probabilities, okay? And so how does that work? So if you want, for instance, the probability that x is between A and B, this is how I use round brackets. The book does it differently. So you would find that density function that goes with it. You need this, and you integrate over there. And this is an awful description in Ross. I mean, it's just terrible. Because when you take these and you study probability at the next level, whatever, you know, that they don't use this approach. I mean, because he's saying that you could, if you want the probability that x is an element of B, then you don't write this down. This is bad. But you have this similar. See, this is not necessarily an interval, but it turns out that the Riemann integral that you learned in calculus is woefully inadequate for handling the integrating over arbitrary sets, more general sets than intervals. Woefully short. Okay, so this shouldn't even be in the book. You should just stick to intervals. Okay. We learned about that stuff as a first-year grad student. Okay, so that being said, so you need this density function. So what do people like to compute? Well, first of all, if you go from minus, you need a condition here. If you go from minus infinity to infinity, you should get 1, okay? That's a condition. It's the normalizing condition. What else? Well, we like to compute expectations. So what's the expectation of x? What's the definition? X times, now the density function, dx, okay? But what if we want some function of x? Okay, this is analogous to what we did in the discrete thing. So how do you do, what if you want the expectation of some function of x? Well, it's what happened before. G of x, f of x, dx. Now I'm going to ask you guys a hard question, but if you've been reading the book, under what conditions would this guy just completely drop out? It just turns into a 1. Maybe that's too much of a hint, but when you don't see the function there, what does that mean? That density function, what you're looking and all of a sudden it ain't there, and it's just a 1 there.
Oh.
Or constant. What does that mean?
Well, the integral becomes really easy to solve.
Right. But what would cause that density function you're looking for? Like, where's that density function? There's nothing there. It's just a 1. what would cause that to happen?
Like the uniform distribution.
Yes, exactly. So if
Oh.
you had the uniform distribution, say from 0 to 1, well, it's high ones because you want to have area 1. The density is just 1. It's there, but they don't write it, so it's very confusing when you're working out problems. Okay. By the way, if the density function was from alpha to beta, then what must be the height of it? How tall must this be? Because you want the area.
Trying to do it in my head, but I want the area to be 1.
Yeah. Beta minus alpha. So you will see, in that case, you'll see the 1 over beta minus, the density is 1 over beta minus alpha. You'll see that, okay? Wait a second, did I even do this right? So I want beta minus alpha. Oh my goodness. I want this times that height to be 1. I need 1 over beta minus alpha. Hold on a second, guys. No. No. All right. Right, I want the product of this
So
to be 1 over.
I'm a little confused.
It has to be 1.
You're talking about.
Okay, let's do a concrete example. So
What
if
do you
I'm
mean
going
by
from,
it goes to 1? Then I might have.
well, the area has to be 1. This area has to be 1. So suppose I go from 2 to 5.
So you're saying that f of x after it's integrated is 1, basically.
Yes. Right.
Okay. I was.
Well, I can integrate because it's a rectangle. I can get the area. I don't need
Okay,
to
I thought you
integrate.
meant that f of x just always equals 1.
No, okay, that's a different issue. So if you have the uniform distribution, say from 0 to 1, f of x is 0 off that. 0 off it this way, but here between 0 and 1, it's 1. So sometimes if you're hanging with stat people, they would say the support of this density function is between 0 and 1. You know, the support means where it's not 0. Okay, just so we're on the same page, we talk about density functions in general. What other property do they have which I didn't state? What property do you think they should have? Well, here we have a density function, right? Here we have.
Can they never be negative?
Yes.
Okay.
Right. What would be wrong with that?
Negative
You can't have like a
probability.
negative probability.
Right.
Weird.
What would that mean? I mean,
That's a good question.
what would that mean if you had a function? I never drew this before, but what if you had like this? If you took the probability from here to here, you would end up with some negative. I mean, is that must be? It's like predestination or something, right? No, it doesn't sound. It sounds too wild to be true, you know. Okay. Okay, let's try to compute an expectation. This is going to be difficult for me because I'm not very sharp today. So, what was that stick problem we were working on? Let's see if I can recall that. Have I used up all the time all this BSing? What was the stick problem? Okay, if you weren't here on Thursday, this is going to be very confusing. But somebody who was here, what was the issue? You have a point somewhere on this stick, and you set that point in advance. Okay, so that's sort of fixed. Say you set it here, point P. Now you're going to break this stick at a random place, randomly between. I guess it has to be properly between 0 and 1, right? You don't want to have the stick back again. Right? It doesn't make much sense. But anyhow, the question is, what is the expected length of the part of the stick has two broken, it's two pieces now, right? Of the piece that contains P. And we sort of, I think Ethan sort of gave a reason or a symmetry, or maybe it was saying, but some sort of
I
reason
was talking about symmetry.
yeah, you want it to be in the middle. And that doesn't,
I was saying, I wasn't saying that you want to be in the middle. I was saying that if P was in the middle, that would be equivalent to just figuring out the expected length of the longer stick, or the longer, stick after it's been broken.
okay, that's fair enough. But there's still a question. Maybe
That's not the answer.
It's not.
Or,
Yeah, right, exactly. The answer is okay. There's still this question: what's the expected length of the? It seemed to me if you put P in the middle, it's symmetrical. I know, but what's the expected length of the piece that contains P? I mean, there's still a question: what is that number? It depends on P, right? So we bring in U, and U is uniform 0, 1. So that's a uniform random variable. It's a simple thing to get wrap our heads around, right? It's just a useful thing in science, I've noticed, computer science. But anyway, we got this uniform 0, 1, and that could be anywhere. So it could break anywhere. So if it breaks here, if that's where we're going to put U, or it might break on the other. There's really two cases here. It could break. It could break on that side of P someplace, or it could be breaking over here. So this is an interesting thing here, and it's the real stumbling block has nothing to do with the math. It's a question of how do we define the function that tells you the length of the substick containing P if you break at point U. That's really what it is. And it turns out that function is what do you call it? Schizophrenic function. It changes its character depending on where.
What I'm thinking, like I'm trying to do the problem right now, is I'm trying to set up a piecewise function.
Yes.
So if U breaks right here, this is the length of the stick.
Exactly.
But it's the other side, yeah.
I think schizophrenic is the word I use for piecewise. That it abruptly changes its character.
Oh, is that what you mean? Abruptly?
Yeah, I thought that some teachers use that. Yeah.
Standard right now is piecewise.
Okay.
That's what I've mostly been hearing.
So, So I'd like to know the length of the piece that contains P. So let's see. So it depends, right? So if U is less than P, there's two. So let's take the case U less than P. It breaks here. Then what is the answer? Well, it's pretty clear. If we broke it here, the piece would be 1 minus U. If we broke it over here, and this is the case that P is less than U, so U is greater than P, then let's check that out. Let's check if this is the case. So U is greater than P. So what's the length? It looks like, to me, the answer looks like.
It looks like U.
Looks like U. That's nice.
Yeah.
Of course, I didn't write it clearly. So I think this is right. It's easy to get it completely reversed, but I think this is. So what AIM is doing is probably trying to graph this. I didn't even think about doing that.
No, at this point, I'm trying to do an expected value.
Oh, okay. So you're done with representing the function. So E.
Yeah, I got that.
Of what is it? Of this is a function of U, right? P is fixed, but that's a function. So E of that, so I got to use that theorem. So you go minus infinity to infinity, that function times the density function for U. What's the density function for U here? Well,
Quick question. Why are we doing infinity to infinity? Or minus?
that's the definition of expectation.
We're going to change it because it's only defined on certain places. But
Right. So
yeah.
I need to. I don't know how to write that density function for U.
Well, isn't it just the uniform?
Right. But I want to make sure that this is the definition. So here it's. I don't know. I don't have to specify, but I know that it's between 0 and 1. It's going to be 1. So then I can drop this if I go between 0 and 1.
Oh, so U is just 0 for everywhere that's outside of 0 and 1.
Right. But I want it to be. I'm trying to get the general formula front and center. Right.
Okay.
This is the density function for U.
Now I understand why it goes from that. Okay.
Okay, but now you see now the changing face of LP of U. So if we're going, so let's see. So if U goes from 0 to P, so U is less than P, then the function is 1 minus U. However, okay, and then it changes if we go from P to 1. So this is U bigger than P, it's U. So what I need to do is integrate this. And I've got to make sure that I didn't blow it. If it's why I didn't put my DUs, I hope that doesn't offend somebody who took calculus.
I'm just a little offended.
Because I know the teachers say do that or you lose points. Some teachers they don't. Okay, so let's just make sure this is correct. Maybe Ames already passed this stage of the problem. Okay, so let's integrate that. Let's integrate it. So what do I get here? U minus U squared over 2 from 0 to P. I should put parentheses. I don't like to gun things up. And then it's plus what? Plus U squared over 2 from P to 1. So let's make sure, what do we have here? So this is P minus P squared over 2 plus 1/2 minus P squared. Uh-oh, this doesn't look like what I got before. So what is it? So P minus P squared plus 1/2. I don't know. Well, it's
I got that too.
1 minus P plus. So if we're talking about trying to, okay, so that's the expectation. But if the interesting thing is, if we're trying to maximize this, in other words, we don't want the short end of the stick. I mean, we want to get the expectation as large as possible, so that the part that contains P would be as long as, and the average as long as possible. We know how to do this because we don't need any calculus. What we need to do is to maximize P times 1 minus P. And how do I know what that is?
That has to do with like finding the area maximizing the area of a rectangle with a specific perimeter. It's usually a square, so you want P to be equal.
Right. I'm trying to recall why that is. So this is.
I mean, if I'm allowed to use calculus, I can tell you why.
No, we don't allow that in this class. we don't allow it. So, how do I know it has specific perimeter? Because
I just know that from you take a string and because it has a specific perimeter.
Yeah,
so.
no, I know. Yeah, string things. Okay. Sorry, you guys. It's been too long.
If you make one
Yeah,
side
you-
really long, then there's going to be no area in it at all because it's stretched all the way out. And
If
it's
you
just,
take p equals a half, take my word for it, it's the max. So you get a 1/2
Yeah.
times a
so
half.
it is when you put it right in the middle.
Yes, yeah, I mean, well,
Funky.
well,
And then the
A plus
expected
the
value
derivative,
is
so I
going to
mean,
be 0.75.
P minus p squared. P minus p squared, what's the derivative? So it's 1
That's okay.
minus p, and you set that equal to 0. No, 1 minus 2p, you set that equal to 0, so I end up with p equals a half. It's the critical point, and you can see that it's going to be a maximum. So anyhow, but more importantly, it tells us.
Oh, that's what you mean by calculus. I was like, yeah, I get it.
Okay, so what do we get here as the answer? So by choosing p equal to half, you end up with 3/4. So the best you can do. So the best is 3/4. It's a little bit impressive. I mean, at least that's what I'm getting right now.
Cool.
Okay, about the string thing. Did you guys do Queen Dido's problem in calculus? Okay, well, that's interesting. Okay, are you guys good with this, or can I'll stop and check the. What's my time situation?
We're basically out of time.
It's the story of my life.
Okay.
The story of my life. You guys got plenty of time. Use it wisely. Okay, well, I just want to show you Queen Dido's problem, and since it got the string got mentioned. So if you have two fastened points here, and you have a certain amount of string, how do you maximize the enclosed area? So in other words, this would be like a shoreline, and you have a floating pen or something like that, floating corral.
Oh, like, explain what?
Okay, so you have some, like you say, a fixed amount of string, and how do you position or place or the string so that you're enclosing the maximum? So you don't need to enclose this area
Those endpoints
because
are.
that's land. But here I got the blue thing. This is water over here. Long the problem's been out there. I think Queen Dido might have been an Egyptian, and she counted like an Egyptian. So this is way old. Okay, they somehow knew of the problem.
What are the constraints? Do the ends have to touch, or?
No, here's one end and here's the other ends. And here, let me just draw a piece of string.
I have
Okay.
no clue. Can you just give an example configuration?
Well, you can.
Yeah, I don't understand what's
I have
being
no clue
enclosed
what you're
here.
saying.
Oh, you have to make an enclosure here, like you could. I suppose you could do that with a string,
Uh-huh.
But you want
So
it
it
to be
has
as
to be
large as
enclosed.
possible. Yeah.
Is that a
one-
limited size for how long the string is? Is that what it is?
Yeah. The constraint is
Okay.
the length of the string.
Then wouldn't it be a semicircle?
How do you know
I mean,
that?
I don't know.
How do you know that? So
Because circles are always the small, like, what's it called? A circle is the greatest area to, like,
enclosed with a certain
yeah.
perimeter. Right, but it's a little more interesting here. So when you say semicircle, you mean what?
Oh, I see what you mean.
What do you mean by semicircle? You mean like
because we don't have to worry about the shoreline.
like that?
Yeah.
Okay, but that's for a particular length. What if you had more string than that?
Okay, well, if you have more string, you can make whatever shape you want. Like, I'm confused by the question.
Well, okay, when you said semicircle, I wasn't sure. What you mean. This technically is a semicircle. What if I had double that amount of string? What shape would you?
Oh! I see.
You're right for a certain length of string, but what if you had more, somewhat more?
Then would it be an ellipse?
No, I think it would be a circle that is cut off at a certain point, basically. What am I trying to say? I don't know what the technical word is for
You're right. You're
what
right.
I'm saying.
Can I draw what I think you're saying?
Yeah.
God, this is hard for me to do because
Oh, I see. Okay.
it's that part of a circle. And they actually, apparently, this was a problem, back in ancient times. It's because it's associated with this figure, this figure in ancient Egypt. I think. Of course, if I'm all right, somebody's probably already Googled and said, no, that was a Greek thing, Queen Dido. I don't know. But anyhow, how to prove that it's a circle? That's an interesting. I think this is called the isoperimetric problem in math nowadays.
That's so
This is an
cool.
interesting thing. It's, with the calculus, 150A, 150B. How do you prove that it's not that trivial that it's going to be this shape?
That's
It's a
interesting.
legitimate calculus problem. There's a bunch of them. Like the the Brachistochrome problem? Yeah, Brachistochrome? You guys know that, right? If you don't know that, can I take 1 minute more of your time to show you?
Go for it.
If not, just
My class starts at 2, but I need to get there.
the Brachistochrome problem is fundamental. Okay, it's fundamental, even in physics, especially in physics. Very easy for me to explain to you. It's a lot easier than that one. You have. Here's the bottom and here's the top, and you want to draw a ramp to roll a marble down, okay, or actually a bead on a string. But let's just say you roll a marble down. I played with marbles when I was young, before I lost my marbles. But I mean, you guys, everybody played with marbles, right? Come on, just admit it. Hopefully nobody ate one. But anyhow, so what ramp would you make? What shape of a ramp so that when you release the marble from here, it gets down to here in the fastest way possible? If you didn't take calculus, what would be the answer? Somebody would go what? If you didn't
You might
take
think it's a straight line.
because why?
but-
Because there's this old saying: the shortest distance between 2 points is a.
It's a straight line.
Why
But
is
if
that?
you want gravity to help you,
Why?
because
is
gravity
nice.
accelerates.
Well, first of all,
Oh,
what's
wait.
wrong about the shortest distance between 2 points? What's wrong about that? On the Earth, if you want the shortest distance from LA to San Francisco, it is not a straight line. You'd be
Yeah.
tunneling, a lot of tunneling. No, that's not the shortest distance. So we know from common sense it's probably not a straight line. But why is it how should you do it? Now go back to your marble days.
You want to make a curve from the top and have that curve go. Yeah.
I'm trying to think of why that
Why?
works.
Why? You seem to know. You know the answer, but why do you know this? Maybe you saw it somewhere, or you have a feeling.
No, okay. God,
I
what
feel
is
like
it
it has
called?
something to do with maximizing the amount of time that it's on the. No, not time.
Minimizing.
Did
Yeah,
you say
time.
like to get it to go the fastest, or to get it to get to the end fastest?
To the end fast.
Okay.
It's a race. It's a race from the start to the end.
You want to have the maximum acceleration at the start, so that the total time of travel, so that the speed is increased. If the speed is increased right away, then it's gonna, then like the rest of the journey is gonna go by way quicker, basically. I don't know how to.
Okay, you're right. You have it. I think, Amy, you were saying something similar, that you want to pick up speed quickly and then you can shoot across. You're going really fast, you can shoot over here. To prove the shape of it, and to find out what the shape is, it's a really interesting answer, okay, what it actually is, the shape is. But to prove that is an exercise in calculus, okay? And old school calculus books from 1930 may have it in there, but the new ones don't touch this because it's delicate, okay? Some of these applications of calculus are really tricky, But just not to hold you up any longer, but it turns out that the shape, and I don't know why, I just remember it, is a cycloid. You guys remember what a cycloid is?
Nope.
What do they teach in calculus? Okay, if you take a circle and you put a point on a circle, okay? So the point's on the circle, this guy.
Yeah.
And if you roll the circle like this, what path is that point going to?
Oh wow.
It's going to go. I don't know exactly. I'm not good at this, you guys. This is hard, but I don't know. But it's something like this. But anyhow, that's the shape you have over here.
Wow.
Okay, it just so happens, right? Nobody would have known that unless you do the calculus. To me, these are legitimate uses of calculus. You know, because you can't without calculus notation and chain rule and stuff like that. You're not gonna. It's gonna be just impossible. I'm surprised they didn't at least mention the Verkrister in old school clocks. It figures in clocks to keeping clocks. You know, when the spring winds down, when they have less impulsive force, you know, old school clocks to make them regular, you know, in time. This somehow this concept is critical. You know, before digital stuff. That's only two problems. I mean, the calculus is full of. If you look at an old school book, it's full of stuff that, you know, it's really neat. I mean, calculus, the real calculus is neat. The way it's taught with just one formula after another, it's not. Oh, you found something on Verkrister. I can't.
Yes, exactly. It's on the Verkrister. I'm like, oh, I've seen this before, and I also know like an interesting thing is it would take the same amount of time to get down whatever height you were at. So like, you could.
Oh. I didn't even know that. So if you started here, it would take the same amount of time.
Yeah, exactly.
I didn't know that. I'm
Oh,
glad
that is cool.
Maybe
Because
that has
you know
to do
you would
with
still
the
need to
clock.
have an acceleration to get there. So yeah, it's the same amount of time.
Maybe that's the application to old school clocks.
Right. The video that I sent has they actually construct one and they test it out, and they do in fact all get there at the same time.
Well, you know,
kinda
there's
cool.
a problem.
Yeah, you could make a clock out of that.
Yeah, but there is a problem. The marble has what's it called? Moment of inertia. You know, some of the energy goes into rotational spin, right? That messes this up. Technically, you
Oh,
on a wire because you don't want to add. How to say? You want it to slide down without friction, and you don't
yeah,
want to.
but then, well, if it's without friction, I mean, you could have like a super slippery slope and a marble that has like no friction against
Oh,
it.
okay, just slides. Okay, that's fine.
Yeah.
But marbles tend to, when it starts doing that revolution thing, some of your energy is going into its spin rather than its translational movement, and you don't want that to mess this up. So I lied a little bit about the marble. Usually they say it's a bead that slides down. You know.
That's really cool.
The way that we did this in like my high school physics class before, because my high school is super weird. We take physics before we do calculus because my professor couldn't explain it with calculus. She took a string that was like the exact like arc length, and she hung it between the 2 points, but she made the points like the same height so that the string would follow that exact Verkrister curve. So you can actually find the exact same curve that you need for any distance between 2 points by using a piece of string that's the arc length.
Okay, hold on a half second because something's confusing me. Because that's called a catenary cut. Sometimes you have here's a holder, and you have a string between them.
Yeah.
That's a catenary, I think. Catenary. And I didn't know that was a Verkrister curve. It's funny how a lot of these things are related.
I think it's only if you use like the correct length of string was like her whole point, because she was just like, you need calculus to figure this out, but you guys don't know calculus, so I'm gonna do this.
That's cool.
Let's see. So if you have the correct answer, it's a catenary cut, and the catenary cut used to be they would from mountaineering tents they would make them so that they would drape this way. Apparently, it's pretty strong or something when you guide out. It's a ideal kind of shape for the tent. If it's a mountain, you know, we're talking about serious winds and stuff like that. And snow load, you know, stuff like that. Catenary cut is the best. They used to have to pay more for that. But I think nowadays the materials are so strong, it doesn't matter what shape it is. Well, you guys,
Gotta go to my next class. Take care.
Thank you for all that. I'm sorry if I went too long. I appreciate
It's
it.
interesting.
Okay, you guys.
All right. Well, thank you, Professor.
Oh, thank you for attending. I really appreciate it.
Of course. Later.
All right. Bye.